Lesson 30, activities. We'll jump into part A. In order for the mean value theorem to be applicable, we need the square root function to be differentiable on the open interval 0, 4. Is it, and how do you know? So the square root function, we know what that looks like. Looks like this. It is smooth, it is continuous, and it is differentiable everywhere it exists, except for the one spot where there's a vertical tangent line, which is right there. It's the only spot where the function is not differentiable. Fortunately for us, function doesn't need to be differentiable at the endpoints, only just inside of those endpoints, right? Not including 0. So we'll just say the square root function is differentiable everywhere it's defined, except at x equals 0. Remember, the only things we're looking to avoid in terms of not being differentiable are corners, which the square root function has none, and vertical tangent lines, which the square root function does have, only at x equals 0, and then points of discontinuity, square root function doesn't have any of those. Part B says we're going to calculate the slope of the secant line on the interval 0 to 4. It's a closed interval here. It's not a big deal that it was open in the differentiable part of the question, but we're looking for slope of secant line. So again, change in y over change in x. F of b minus f of a divided by b minus a. It's okay if you swap the 0 and 4 on top and bottom. So this is the square root function. So square root of 4 minus square root of 0 over 4. 2 minus nothing over 4, which is 2 over 4, or a half. Now we find the derivative. Thinking of square root of x as x to the half. Half comes down. Copy the x, subtract 1 from the power. It's fine to stop right here, but we're actually going to end up doing some algebra on this, so it's actually in our best interest to make this a little more user-friendly. All right, 1/2 makes a 2 on the bottom. X to the negative 1/2 is really x to the positive 1/2 downstairs, and x to the positive 1/2 is a square root of x, but it's downstairs. And we do need a placeholder upstairs, so it's 1. Okay, and then what we're looking to do here is set the answers to b and c equal to each other. So it was a half and 1 over 2 root x. And we're going to solve for x, and whatever we get for x is the magic c that was guaranteed by the mean value theorem. So let's go ahead and cross multiply here. 2 root x equals 2. Root x equals 1 by dividing by 2. And then square both sides, and we just get x equals 1. So that's the value of c. And then it says find the y value. So this is just f of 1, and that's the square root of 1, which is 1. So that means that the point guaranteed by the theorem, in this case on the interval 0 to 4, is 1, 1. Then you can take a look at a picture, graph this thing on your calculator or on GeoGebra, draw in the tangent line at the point x equals 1, and go ahead and draw in a secant line connecting 0 and 4, and you should see that they are parallel to each other. Number 2, does the mean value theorem guarantee the existence of a special point on the graph of f of x equals 1 over x minus 4 on the interval 3, 6? So what we're looking for here is to see whether this function right here has any problems, or is it differentiable everywhere on the interval 3 to 6? Now this problem involves division, and we know that we cannot divide by a very certain number. We cannot divide by 0. And so the question is, what value of x makes us divide by 0? And the answer here in this case is 4. So we would say that f is not defined at x equals 4. And so therefore, because it's not defined, therefore not differentiable at x equals 4. And so that means that this function is not differentiable on the interval 3 to 6. So that means that the mean value theorem does not apply. The mean value theorem is a promise. If you hand me a function which is differentiable on an open interval, then the mean value theorem promises that there is some number c where the tangent line is parallel to the secant line. But that promise only is in play if you hand the mean value theorem a function that is differentiable. And this function is not differentiable, and so the mean value theorem isn't even going to pay any attention to us. And it's saying, I'm only making a promise under the condition that you hand me a differentiable function. So the mean value theorem doesn't apply. It's not to say that there isn't a point C where the tangent line is parallel to the secant line. There very well could be. And in fact, I think we're going to make some examples up in this activity where we have to find places where the conclusion of the mean value theorem is satisfied, but the hypothesis is not. But all we're saying here is that the mean value theorem makes us no promises for this particular function on the interval 3, 6. Okay, we're going to use the racetrack principle to prove that for x bigger than or equal to 0, one of these two things is true. Either sine of x is less than or equal to x, or x is less than or equal to sine of x all the time when x is bigger than or equal to 0. Hopefully, if you think about the graphs of sine of x and x, you should be able to convince yourself that one of them certainly cannot be true. So if we draw a quick sketch of sine of x, and we draw a graph of y equals x. So if I'm only looking when x is bigger than or equal to 0, so that's out this way. Okay, so for sure, x less than or equal to sine of x, no. I mean, it could be. I mean, like the way that I've drawn it, the orange thing is underneath the blue thing for a little bit here in the beginning. But eventually, the orange thing is going to be way above the sine, right? But the way that I've drawn it, this one is also not true. Not for every x, right? It looks like the way that I've drawn it, there are some x's where maybe the sine of x is just a little bit above the x value, the y value, y equals x. But according to the this example, actually, the way I've drawn it isn't accurate, right? Like if we're trying to prove, I mean, it's for sure it's not that. So this must be true, which must mean that actually the y equals x line, even though it's really close, it must just barely sneak ahead all the time. So it might not be something you were aware of unless you really focused the graph in near the origin where you compare y equals x and y equals sine of x. But let's take a look at this step, the process here, and we're going to prove that sine of x is always less than or equal to x if x is bigger than or equal to 0. Okay, so we've got our two functions. G and h, sine of x is one of them, x is the other one. It doesn't matter which one is which. Are g and h both differentiable on the interval 0 to infinity? That's the interval because this problem is asking us about something where x is greater than or equal to 0. So that's equivalent to 0 to infinity closed. So are they both differentiable on that interval? Sure. G and h are differentiable everywhere. Yep, sine has no problems, x has no problems. Okay, let's find two derivatives. G prime of x is cosine of x. H prime of x is 1. Now let's write an inequality that relates these two derivatives that we wrote. I'm hoping that one of these is always less than or equal to the other. So in this case, cosine of x compared to 1, well, we know cosine is trapped between -1 and 1, so that means that cosine never gets any bigger than 1. It does get equal to 1 at the top, but it's never any bigger than 1. So that means that in our case, g prime of x is always less than or equal to h prime of x. Hey, that's great. That's actually one of the parts of the hypothesis for the racetrack principle, right? This says that Goethe is running slower than Hertz all the time. Let's evaluate g of 0 and h of 0. Remember, g was the sine function. Sine of 0 is 0. H of x was just equal to x, so h of 0 is just 0. And so that means that g of 0 and h of 0 are equal to each other. This is saying that Goethe and Hertz start the race at the same time at the same spot. And so these are exactly the conditions of one of the parts of our racetrack principle, right? Let's go back. Here we go. I think we're looking at the part A1. So our interval was 0 to infinity. We convinced ourselves that g prime is always less than or equal to h prime. on 0 to infinity, and that g of 0 is equal to h of 0. So that means that, and also that our two functions were differentiable. And so therefore all of the conditions of the hypothesis have been met, and our conclusion is therefore that g of x is less than or equal to h of x everywhere from 0 to infinity. Notice again, it's specific to this one. They're both starting at the same spot. If they ended at the same spot, the inequality flips over completely. So you got to be really careful that you know which part of the racetrack principle you're applying. But ours is this one. G of x is less than or equal to h of x all the time. Have the conditions been met? You bet. What's the conclusion? The conclusion is that g of x is less than or equal to h of x for all x on 0 to infinity, which in this case, just rewriting g of x as sine of x less than or equal to, and then h of x was really just x. And this is exactly our conclusion. Sine of x is always less than or equal to x when x is on the interval 0 to infinity. So I will come up here and I will say that this now is a poorly drawn graph, right? Because now we see that that orange line is always above the blue sine curve as long as you get to the right of the origin. Okay, number 4. Same as on the previous problem, but now we're not going to give you the steps laid out. So either 1 plus ln of x is less than or equal to x all the time on 0 to 1, or x is less than or equal to 1 plus ln of x all the time on 0 to 1. Okay, so first thing to do is to let g of x equal one of the two sides of the inequalities and h of x equal the other one. Now, honestly, it makes no difference which one you pick. The fact is the g and h do mean specific things in the racetrack principle, the thing we just looked at on the demo. The g and the h, you know, like in both cases of the theorem, g prime was less than or equal to h prime. And in both cases of the theorem, we end up comparing g to h with an inequality. And so if you were to swap g and h here, it would be totally no problem, you know, to swap g and h here, and that's fine. But you do just have to be careful if you happen to pick g and h different from the one that gives you this order for the derivatives. So if you want to go out of your way to try to make sure you pick g and h to be in this order when you do the derivatives, that's okay. I'm just going to pick the first one for g and see what happens. Okay, so left-hand side up here, that's going to be my g. This is going to be my h. So 1 plus ln of x, and just plain old x. Okay, so what we need is for these functions to first be differentiable on the interval 0 to 1. And so the x function is differentiable everywhere. Now, ln of x is differentiable where it exists. Where does it exist? Remember, the ln graph looks like this. And so it doesn't actually hit the y-axis. So it doesn't exist at x equals 0. But hey, x equals 0 is not part of our interval. So we just made it. So I will say that g and h are differentiable everywhere they exist, or they are defined, including on the interval 0 to 1. Okay, so we'll continue to follow the outline from the problem right up above. So the next step for us was to find derivatives of both of these things. So g prime of x is equal to the 1 plus goes away. Ln of x has a derivative of 1 over x. And the derivative of h is 1. Okay, and then the next thing we do, again, following the process from up above, is to write an inequality that relates these two things, 1 over x compared to 1. So is one of these things always less than or equal to the other? You've got to be really careful here. If, for example, you pick like x equals 500, and you put it here, and you put it here, but there's no x's to put it in over there, then 1/500th is definitely less than 1. And if you pick x equals a billion, 1 over a billion is less than or equal to 1. So we might be tempted to say that the inequality goes this way. but you got to make sure you're picking numbers in that interval. And if we pick a number in that interval, for example, a half, I'll just do this on the side and then we'll erase the evidence. G prime of a half is 1 over half, which flips around and gives us 2. And H prime of a half, well, H prime of anything is 1. So now which one is bigger? Oh my goodness, the G prime actually ended up being bigger. And you should take a moment to convince yourself, but it wasn't just special, anything special about the half that I picked. You pick any number between 0 and 1, and the G prime is going to be bigger than the H prime. All right, let's take a look again at our racetrack principle and see if G prime bigger than H prime was the direction and the theorem. G prime is less than or equal to H prime. G prime is less than or equal to H prime. Shoot. Okay, like I said, you are welcome to just pick G and H willy-nilly like I just did, and then just very carefully apply the theorem, but know that the letters G and H have swapped from what's given on this page. But I'm actually going to do something that I think is easier. I'm going to backtrack, and I'm going to change my definitions. I'm going to say let h of x equal 1 plus ln of x, and let g of x equal x. Everything we said about differentiability is still true. We're going to hide the evidence over here. And we're going to change this is now h prime, and this is now g prime. And on the interval 0 to 1, g prime we discovered was less than or equal to h prime. I guess what we saw was that h prime was bigger than or equal to g prime, but I'm writing it in the same exact way that is written in the racetrack principle on in the demo. Okay, next thing I think we need to do is either plug in like the starting number into both of the original functions, or plug the ending number into both of the original functions. Okay, plugging the starting number is actually not even a possibility. First of all, it's not included. Second of all, ln of 0 doesn't exist. So I guess we're not starting in the same spot. We must be ending in the same spot. So let's plug 1 in to both of the original functions. G of, I guess I'll keep h first here. H of 1, remember now h is the 1 plus ln function. 1 plus ln of 1. Ln of 1 is nothing, so that's equal to 1. And then g of 1, g is just the x function, so this is simply 1. And what do you know? We're tied. So that means that g of 1 is exactly equal to h of 1. And is that the start of the race or the end of the race? This is the end of the race, right? And so our conclusion, I'm not going to go back and look at it, but our conclusion here, we saw that g was running slower the entire time after we redefined our g, and that they end the race tied. So if they end the race tied and g was slower the entire time, that means that g must have been ahead the entire time. G must have been ahead the entire time. So by the racetrack principle, g of x is ahead of h of x. I'm going to put an equal sign there just in case they're tied. I mean, they are tied at the end on the interval 0 to 1. That's just copied from the given. And then finally, we'll just rewrite that inequality, but g of x, remember, was defined by us early in the problem. G of x was x, and h of x was 1 plus ln of x. So any place on the interval 0, 1, x is bigger than or equal to 1 plus ln of x by the racetrack principle. And you can check that. You can graph it on your calculator if you want to see that. Okay, next page. There are lots of possible answers for these. I'm just going to give one example for each, maybe a second example if the mood strikes me. But there are lots of correct answers here. So if you're not sure, ask each other, ask your instructor. Make sure we understand what we're doing here for the hypotheses and conclusion stuff. So we're going to draw a picture that satisfies the hypotheses and the conclusion of the mean value theorem on 1, 5. This one's easy. You pick a point right here at 1. You pick another point right here at 5. You draw any function which is differentiable on the entire interval, about like that. And that's it. And so to really convince your instructor that you have found something that satisfies the hypotheses in conclusion, you should probably draw in the secant line and then go ahead and draw in the tangent line that's parallel. So for example, maybe like right there, but actually there's one more over there. That one wasn't quite good. Maybe that. And actually I think there's maybe even one more like right in there. So it looks like there's probably 3 different points C that work for this one. And that's okay. The mean value theorem doesn't say there's only one value of C. It says there exists some C. Okay, we want a function that satisfies the hypotheses, but not its conclusion. This is simply not possible. As soon as you satisfy the hypothesis of the mean value theorem, you automatically satisfy the conclusion. Again, the mean value theorem is a promise. If you find a function, if you deliver a function that satisfies the hypotheses, the mean value theorem promises that the function will automatically satisfy the conclusion. You can't have the hypothesis satisfied and not the conclusion. Okay, now we want something that satisfies the conclusion but not the hypothesis. Conclusion but not the hypothesis. All right, so for this one, here's my technique. I'm going to put a point at 1, put a point over here at 5. I am going to just draw something nice, something differentiable. So for this particular function, it satisfies the hypotheses and the conclusion. I'll go ahead and draw in my my secant line, and then I will eyeball where my tangent line is, something like that. I've got the magic point right over here. That's your C. But this one says you don't want it to satisfy the hypothesis. You want the conclusion, which I've got, but you don't want the hypothesis. And I have the hypothesis solved. So how do I make it not satisfy the hypothesis? Well, I can do lots of cheesy things. I can take my little eraser, little list eraser. I can take out one point that has nothing to do with anything, as it's really far away from the magic point that worked. So technically, this function does not satisfy the hypotheses of the mean value theorem because this function is not differentiable everywhere between 1 and 5. Turns out it is differentiable nearby the only spot that matters, which is this magic thing here called C. So we still have the C that works, even though I've gotten around the hypotheses with a technicality. Okay. All right, so that one's good. You could also, if you don't like that, you could do something similar. But then someplace in the middle, let's actually get rid of part of this here. Let's make it so that we, sorry, I should just do this one the way we did the previous one. So we've got our 2 points at 1 and 5, and then I got that, and then we draw our secant line, and then we draw our parallel tangent line. And then to make sure I don't muck up that point right there, but I can do anything I want far away from that point. And so for example, get my eraser. Nope, that's not my eraser. Get my eraser again. I'm going to get rid of like this entire ending part right here. And I'm going to make it so that this thing changes abruptly before going back to the same point at the end. And so this function is continuous everywhere, but not differentiable on the interval 1, 5. Because it's not differentiable at the corner. But still, I've got my secant line and my tangent line that work. Okay, and then finally D, I want something satisfying neither the hypotheses nor the conclusion of the mean value theorem. All right, so I've seen students come up with lots of different options here. One of my favorite, I think, is the cheesiest one. I'm going to show you that one first. So here's my secant line. There's my tangent line, blue dot right here at the winning point. And so what I've seen a couple of really clever students do, they say, okay, we're just going to go to that one spot that is the one magic one that works. I'm going to put a hole right there. And so this function doesn't satisfy the hypotheses because it's not differentiable at that hole. It's not even defined there. And also it doesn't satisfy the conclusion because the student did a really cheesy thing and took out the one point that we care about, the one winning point, the value of C that would have worked. I say cheesy, but I really liked it. So I mean that as a compliment. Okay, another possibility here, suppose that we were to go something like this. So I'll put a dot here, horizontal secant line in this case. And then I'm going to fail to be differentiable by making a corner. Let's make that one not quite as flat there. So like this and like that, something there. And so not satisfying the hypotheses because it's got a corner. But there's my secant line. Are there any horizontal tangent lines any place in this graph? And the answer is no, there are no horizontal tangent lines. So it doesn't satisfy the hypotheses or the conclusion. Again, lots of possible right answers there. Ask somebody to check yours. Okay, here's an invalid proof that 1 over x is less than or equal to x for all x bigger than or equal to -1. And we really hope that the proof is invalid because the conclusion is certainly not valid. For example, if you pick, I don't know, x equals half, then this thing right here, let's say 1 over a half is less than or equal to a half. Is it? No, 2 is not less than or equal to a half. So that is a problem. So looking at the proof, you can read through it, pause the video here if you haven't read through it yet. But I will just point out that the problem here is that, where is it here? Racetrack principle means that we have a function which is differentiable on the entire open interval. And so the interval in this case is everybody bigger than or equal to -1. And the function, one of the functions we're talking about is this function right here, 1 over x. Is that function differentiable everywhere when x is bigger than or equal to -1? Well, it's got division, and I know I can't divide by 0, so clearly x equals 0 is a problem for this function. But x equals 0 is right there in this interval. And so that means that the racetrack principle simply doesn't apply. F of x equals 1 over x is not differentiable at x equals 0, which is in the interval. What is this one? -1 to infinity. Just rewriting the interval up at the top as that as an interval notation thing instead of an inequality. So the racetrack principle does not apply. And in fact, that is enough to invalidate the entire proof. I know you've read the whole thing, hopefully a couple of times, but the fact is, it doesn't matter how good the rest of the math is in a proof. If you find one line that is invalid, then the rest of the proof goes out the window. Now, maybe it's possible to fix that small invalid thing and not throw the whole proof out the window, but we don't have to look at anything else in the sentences that are written in this proof. One fatal flaw is enough. Is the conclusion true even though the proof is invalid? So no, I actually answered this one at the start. So no, for example, x equals a half. Okay, number 7, pause the video and read if you haven't done so yet. F of t is our distance from the first toll booth t hours after 12 p.m. We're going to fill in the blanks using data from the paragraph. So it says at 4 p.m. We were, so that's 4 hours after 12 p.m. We were at the first toll booth. And so how far, what's our distance from that first toll booth when we're at the toll booth? 0 miles. And then at 5:15 p.m., so that would be 5.25 hours after noon, we are 100 miles from that first toll booth. Let's find the slope of the secant line connecting those two data points, and we'll go ahead and include units. So it's f of 5.25 minus f of 4 divided by 5.25 minus 4. So, so f of 5.25, so that's 100 minus nothing divided by 1.25. So 100 divided by 1.25. Is that 80? I think that's 80. Okay, part C, it said, we wanted units here. So the numbers on the top of our fraction, 100 and 0, those were measured in miles from the first toll booth. And then the 5.25 and the 4, those were hours. So miles per hour is the units for 80, which could be a problem. The derivative of f represents what kind of velocity, average or instantaneous? So we know derivatives are always instantaneous velocities. The mean value theorem guarantees that there is some c between t equals something and t equals something. Okay, so the t equals are the input values, in this case 4 and 5.25, such that f prime of c is equal to, and then we're going to put a number here. So we know the mean value theorem conclusion said that f prime of c was equal to the slope of the secant line, f of b minus f of a over b minus a. But hey, that's exactly what we did right here. And so 80 is what goes right there. Write a sentence explaining how your answers to part D show the officer either was or was not justified in writing you a ticket. Well, what the officer can conclude using the officer's solid knowledge of Calculus 1 is that by the mean value theorem, I guess we should say this particular f function, the distance function, is hopefully a differentiable function, right? Like your distance between the one toll booth as you drive along this highway, and you plot your distance as your distance increases when you drive along this highway. I think we can assume that that is a differentiable function. It's going to be continuous. You're not going to like blink from one moment to the next and be, like 3 miles apart on this highway at those 2 moments. And I think when we plot our distance, we're just going to get some smooth continuous curve. Unless I guess we get rear-ended or something, but we'll assume that the function is differentiable on the interval 4 p.m. to 5:15. So in that case, by the mean value theorem, there is a time between 4 p.m. and 5:15 p.m. where, remember, f prime of c is the instantaneous rate of change. And the instantaneous rate of change is our velocity, or our speed. Our instantaneous velocity was exactly equal to the slope of the secant line, which was 80 miles per hour. So sometime between 4 and 5:15, sometime between those two toll booths, for sure, we were going 80 miles per hour. And I don't know of any highways here in the US where the speed limit is as high as 80 miles per hour. So I think we are guilty. Next time, leave yourself more travel time and go slower.